Hi, everybody. Welcome to another workshop of our series of workshop for this winter. The workshop is Generalized Linear Regression Models, is introduction actually to Generalized Linear Model that is posted, and it will be introduction here too. So hopefully we can have another part very soon, but as you will see, generalized linear regression model itself might be 2-semester course or 2-quarter, 3-unit course. So it's a lot of material in there. And obviously we cannot cover everything. Okay, so let's start with an overview. By the way, if you want to copy paste some code or something, you can click on I think K, and then is mouse doesn't advance. Otherwise, if you click on the mouse, it will advance. Okay, so and then you can use page down, page up. In the site that I send it to you, the website for seminar, it explains how you can play with I send it again, with these slides. So you can also download it, okay? And the code is also in this website. So I'm going to open it. So if you go to this link, the website is here, the slides are here, you can download it, and the R code is here. So you can use arrow key, mouse click to advance a slide. You can use A to toggle between a slideshow and handout view, which is just all a slide in one handout. You can use K to disable advancing a slide with the mouse click, S and B to make the font bigger and smaller, and F11 to go to full screen and back. Okay. So the R codes for the seminar is here. If you click on that, it's a text file. Okay. So you can copy paste it in the R, or you can right click and download it in your computer. Some of the codes here is only to get the plots that are used in the workshop. So it's not something is very related and you don't have to run it. So I make those codes. And the part that is mostly optional, I put it as commands so you don't have to run it. Okay, so you can copy the code, part of the code, copy or everything, and let me share again my R. And then you can go to the file. This is, by the way, I expect you at least have some understanding on R. You don't have to be expert in R. R script, and then you can paste the codes here. And then you should be able to run the codes if you like to follow the workshop along with me. Okay, I don't need to save this because I already have it here. I don't need this one. Okay. And through the workshop, I will go back and forth to the slides and code. Not much. There is one example. I will go there. Otherwise, other codes are there. You can also copy paste from the page. Let me share my slide again. I'm going to share the whole thing so then you can see my screen when I jump over different. So again, you can click on the slides and open the slides. Okay. So I haven't put table of content. It was a little hard to put the table of content. I wanted to make sure it's able to go to the page. It was taking a lot of time, so I didn't put it there. But you can jump over the page using this. Somehow it doesn't show, it shows part by part, but it's okay. So hopefully I will be able to figure it out how to put the table of content in the first page using R Markdown. Actually, I created this slide using R also. So let's look at the first. I make it a little small so you can see the whole picture. Let's look at an overview of generalized linear model to see what are those. Basically, linear regression model that you might be very familiar with it is kind of generalized linear model. Is very simple form of generalized linear model. And then there is general linear model, which is more general form of linear regression model. So don't get confused the word general linear model and generalized linear model. We are not going to discuss this model. It's not very difficult. It's very straightforward, but it's not part of this workshop. Of course, we go over linear model a little bit as overview. In overall, the most application of generalized linear model is categorical outcome and count data. I put them in two separate because they are basically two different type of generalized linear model. So in categorical outcome, let's start with here. Categorical outcome could be 0 and 1, or only two possible outcome as our outcome. Male, female, admit, not admit, win, lose, or everything that has two possible outcomes. All of these possible outcomes, you can always use 0, 1 to demonstrate them. So, but R really doesn't care in this case, but you can also, but as R treat dichotomous variable also as 0, 1 variable. There is multinomial logistic regression when the outcome has more than 2 levels, 3 or 4 levels. And then for this model, you need to estimate lots of more parameters. We are not going over this model also. And things get more complicated when you go to ordinal logistic regression. There is some assumption that involves here. Ordinal logistic regression has the outcome that is more than 2 levels, because if it's 0, 1, it's already ordinal, so there is no difference. So it's more than 2 levels again, but the order matters. So is 1 to 3 level, or could be something that in questionnaire people answer as satisfied, very satisfied, satisfied, neutral, unsatisfied, something like that, that you have ordered. And then we go to Kant model. In Kant model, basically we start with Poisson regression and we extend it to more general form of Poisson regression. So everything starts with Poisson, and from Poisson it extended to negative binomial, and then to zero inflated Poisson or zero inflated negative binomial, or truncated Kant, censored Kant, and these kind of models. So truncated Kant is the model that you don't observe some values less than some particular outcome. you don't observe either predictors for those or the outcome for those limits. So they call them truncated model. Censored counts is when you observe predictors, but the outcome is censored. We are not going over these models. I just defined them here. And the mathematics of these models are a little complicated. They are usually called, some kind of mixture count models. There is harder models that, and there is zero inflated count model. Harder model is the model that is kind of mix of 0 and 1, and then is kind of truncated count, which doesn't include 0. So in the count part, you don't observe any 0 for the count part. So it's a mixture of two models. The 0 is because of something else. So for example, if somebody goes to shopping or they don't go to shopping, and how many items they shop, right? So if they don't, so 0 is, that means they don't go to shopping. And if they go to shopping, they, assuming they shop, okay? And the number is 1, 2, 3, 4, 5, and more, right? It's a count. But the count part doesn't have 0. Zero inflated count model is the model that has a 0, but there is another 0 that is coming from other structure or other, it has other basically root, right? So the very popular example of this model is people go to lake and how many fish they catch. They might fish, they might go to fishing and they can catch 0, 1, 2, and more fish, but they might not go for fishing, right? So there is another mechanism that causes that 0. So that, you know, it's not always if you have a loss of 0, it's 0 inflated count model. So this is something that you need to remember. And there is other models here. I put beta regression because beta regression is very different a little kind of than the other kind of generalized linear model, but they are complicated model. There are packages in R. You can run those models. There are ways to run them in SAS, Stata. There is good documentation about all those models in the Stata. In R, you know, you have to read the document, read the function, read the paper that the library or that package comes from. So yeah, those are. And there is extensions of generalized linear models that including generalized estimating equation, I put it there, generalized linear mixed models, and generalized additive model. Generalized linear mixed model is when you have kind of clustered data. The data are not independent completely. General estimating equation, you don't care about the within those cluster variation, but there is a structure of covariances and dependency in the data. And generalized additive model is kind of a smoothing function, and those has different story. But they all comes under this generalized linear. Not that these are exactly part of generalized linear model, but they are related. Even linear mixed model is somehow related to generalized linear model, but that's another story. Okay, So that gives you an overview. What we do is this. We look at logistic regression, not completely. Still, that could be a course. We go over Poisson regression with some example and little bit negative binomial if we have time. Okay. There is not much difference between these two models. The mathematics is a lot different, but how to interpret those models and how they get that, those models are very similar. Okay. So before we go to generalized linear model, sorry about that. My internet recently, I need to complain in Cox is getting disconnected. So if that happens, Christine, can you go to the website and when I'm gone, at least share the screen? So that would be helpful. Andy will come back. So again, sorry about that. This is the part that I need to edit in when I want to put the video on YouTube channel. Okay. Basically, what is a regression model? Regression model is the model that you want to explain relationship between two variables. One variable is a response variable or dependent variable, and one variable is independent variable. Or you can have many predictors or independent variables. Let's start with some notation. I'm not going too deep in mathematics here, but at least we need to know the model formula and basic mathematics. So in simple regression model, we have a pair of observation. Simple regression model means that we have only one predictor. The pair of observation can be shown as xi and yi. And these pair, you collect the data for every cases in your study or every individual. In the population that you are interested to study or do statistical analysis. The goal is to investigate the relationship between X and Y. In linear relationship, as you can see from its name, we assume this relationship is linear. Okay, so then we can write the model formula as this way. So y is equal to beta 0 intercept of the line plus beta 1, the slope of the line, and times x, which is the predictor, plus some error part, which is uncertainty, or a statistical part of that makes the model not deterministic, right? So this is uncertainty that exists in the data or in random sample. The quantity beta 0 and beta 1 are model parameters. Sometimes we call them coefficients of the model. And epsilon is the unexplained uncertainty that cannot be explained by the linear model. We can extend, of course, this model by adding more predictors. We still have one uncertainty E, and we have this linear part. Still, this is linear, although we cannot show in if we have more than 2 predictors, right? Then we are going to have to show them in 4-dimensional space, right? So, but still, the relationship is linear because all these coefficients are linear. So there is no non-linear part here, basically. But think about it. If I have x1, x squared, is that a linear model? The relationship is not exactly linear, but still y has a linear relationship to x1 squared. So any kind of those quadratic or square form is you can simply change the variables, change the predictor, and then find the linear relationship with that change variable of predictor. Okay, here again, beta 0 is called intercept, but because we have a loss of slopes, each slope is one slope for each predictors. Notice that for different predictors, I use J index, and J is from 1 to P. Here, for each cases, I use I index, and I is from 1 to N. So basically, if you put the data together, you have a matrix of P plus 1 row, I'm sorry, N row and P plus 1 columns, okay, if you have multiple regression model. And yeah, I explained that here. Another parameter that we are estimating is variance of epsilon, which is sigma squared. That is unknown. And as a byproduct of this linear regression model, we estimate that, which is very important, in fact. Okay. In OLS, we have to make some assumption. The first assumption is, of course, that we assume the relationship is linear. Okay. But that's beginning assumption. We have to make this assumption at the beginning to be able to run this model. This is the model we want to test. Actually, the method that we estimate this parameter is called ordinary least square. By least square method, basically, we estimate those. And that least square method have this assumption. If you look at this model, there is 2 parts. One is a fixed part for given fixed x, and one part is error part, which is a statistic is uncertainty part of the model, and we call that error part. So you can separate the model by 2 parts, right? The error, all the assumption goes on error, right? There is nothing there that is random that we should make. The only thing is that this systematic relationship is linear. This part, though, the assumption is that errors are independent, randomly sampled, with the constant variance for any outcome. So for any outcome, the variation, the error should be constant, or we assume to be constant. Otherwise, OLS doesn't give you a good result. And there is some mathematics. It's not about unbiasedness, but I will explain. This assumption is aimed for two things. First, to estimate the parameters, and second is to make inference. So to make the estimate unbiased, the error mean should be equal to 0. Okay, so if means of error is equal to 0, the OLS estimate gives you unbiased estimate, no matter what. Okay, unbiased means that as you have more and more sample, then the parameters, estimated parameter, get closer and closer to actual value that is unknown, and you try to estimate to actual parameter. Errors are independent. Error have equal variance. These assumptions are necessary to make the correct inference. Basically, these two assumptions makes the variance unbiased. So estimating that variance is also very important. If you don't assume they are equal, then it's very hard to calculate that. And that affects the standard error of your estimate. So if you don't get the correct standard error, you cannot make the correct confidence interval. And then you cannot make a correct inference in statistics. So another assumption, so this assumption also known as homoscedasticity or homogeneity of variance. I'm sure lots of you have heard it. The other assumption, the last assumption, is that error should follow the normal distribution. This assumption is not as important as other assumption, because if you have lots of sample and our sample size is large, then asymptotically everything works out, and then you get the asymptotically unbiased standard, everything will work. Okay, so the T statistics works fine, F statistics, so those depends on the sample size. But if you have a small sample size, then the normal distribution is important. Okay, so this is the assumption of OLS. This is a review. You should already know. I'm sure you know. Okay. In linear model, there is another thing that I showed you. There is two parts. The part that is systematic part or linear part, it can be run. It actually is the mean or expected value of outcome. Okay, given the predictor X. So given predictor X, you have an outcome which is from this formula, right? This is the outcome. I didn't show that given X, right? But it's given a particular X, right? And that Y is a random variable with the variance equal to sigma square for given X, and this sigma square is equal for every Y, right? So if you have multiple predictors, you can write it as this. So expected, in statistics, expected is a mathematical term, is mathematical statistics used for population mean, right? So basically you can think about that as the mean, or what value we expect on average, right? So don't worry about this notation if you don't know it. Basically, mu is the mean of the outcome. For simplicity, I didn't put under here mu of Y given X. So I'm going to use this notation throughout. So mu is basically a linear function of all those predictors, right? And that mean can be any value from negative infinity to infinity, because these x and betas could be any value. So okay, if you also have a question, you can ask if you can share with everybody. I need to stop and ask you if you have any question. So in here, the linear prediction can have any value between negative infinity and infinity. Now that's the question. What if the mean of the outcome, or the outcome has some sort of a distribution that the mean is not from negative infinity to infinity? In fact, in a lots of cases, for example, in Kant model or in a Bernoulli model, the mean is limited, is always positive. And in case of Bernoulli, the mean is between 0 and 1. We will see that in more detail next. So that's why we need to extend this method. And also another thing that we will see. Example of linear regression, I use this data from our OARC statistics website, and is about the school performance and student number of enrollment in a school. So API score is average student performance at 2000, and enroll is number of students enrolled in the school. So if you read the data and look at only these two variables, by the way, again, you can copy and paste this code and run it if you like to run and see the result aligned with the workshop. So this is online, and you don't need to download it. You can just read it from this website. And then you see the variables are like this. So API is somewhere around 500, 600, 800, and number of enrollments. We think that the relationship between enrollment and API score is linear. So basically, this is the question: how increase of number of enrollment in the school change the average performance of a student in the school? Okay. And then in R, we use function LM. It's very simple. There is this notation tilde that give you the relationship between these two variables. We call this model formula, and you can call the data. There are other options here that I'm not going to go over those. Our functions have tens of options. So, and then you run it, you get the summary of, and this is summary, extract this. And remember, R is object oriented. So this M1 that I save here is not data, is LM object, right? When I do summary, it knows that what should it do with LM objects. So it runs the summary based on this argument, which is LM object. And then it gives you the result. So you see the intercept in estimated enrollment, which is negative. That means the number of enrollment has negative impact on the student performance. And then we can interpret this result, right? The estimation of the intercept is this. That means for a school with 0 student, that is performance. That doesn't make sense, right? This is not expected. So usually the intercept is not something that we want to interpret. But here, the enrollment, which is the slope, is minus 0.2, which is, this means that for 1 unit increase or one additional enrollment, the expected API score decreases by minus 0.2. Or you can say for 10 more number of students in the school, we expect on average the number of the API score decreases by minus 2. And another thing that we should sometimes plot that before see the relationship is using a scatter plot. In R, you can just use plot and then use that model formula again, data, or DAT here. And you can call the main and X value, Y value, and then plot it, right? So as you see here, and then AB line model, and I make it blue, is the linear estimated linear regression line that we think it fits the data the best as the linear function, right? So, and you see the slope is negative, it goes down, right? So that's it, that's a linear model, right? Now, let's go to this part. This part is optional, is not very relevant to the workshop. You can just skip it, right? So basically here I showed how the least square, minimizing this least square function, which is the residual, and then I define the component. If you like to see it, is there, you can just see that. And then how it, well, is a lot more in here. So you can write pages and pages about this square and R square and things like that. Okay. And this is also part that you should know that we have to after we run the regression model, we always need to assess the assumption that we make. You know, here the linear model that we ran, it gives us a t-value, right? It gives us a t statistics. Oh, this t statistics is very small. The p-value is very small. Maybe if assumption is a little violated, because my data is large, my sample size is 400, right? So might not be as important, but is important lots of time to be accurate, right? So we need to look at the assumption, and as you see, the normality is not very good, but I said this is okay because we have 400 sample size, right? And then you can see other residuals, leverage, inflation points, and coexistence and stuff like that, right? Okay, which is not the subject of this workshop. Now, this is where we start to think about some extension of linear regression model. By the way, I stop now, and if you have any question, let me see. Anybody wants to ask any question so far? I think this was already a review, so you all know already what are those. No questions? Okay, we continue.
I have a question.
Yeah, sure. Go ahead.
This is just going back to the zero inflated models that were talked about in the chat. I don't know if you plan on covering this, but I just wanted to ask it while it was fresh in my mind. But how do you differentiate between the sources of the zeros? So if a 0 is because I didn't go fishing at all versus I didn't catch any fish, just out of curiosity.
Right, right. We estimate that if we assume there is a mechanism, right? So based on our experience, we know that, okay, first of all, in the data, we see exceeded 0, right? And then we think, why is that, right? Is that a real 0 or it comes from somewhere else? And then we think about, oh, maybe there is another mechanism that makes this 0. In the fish example, we already know based on our scientific experience, right? So we know there is something. And then we can estimate that, right? If we make the model like that, we can estimate the portion that is 0 because people didn't fish. Make sense?
Yeah.
Okay, good. Yeah, the model is a mixture model. So you estimate two model parts. So it's a mixture as a count and a logistic, if you want. Yeah.
Okay, that makes sense.
Sure, sure. Yeah, but we don't go over that. We have a page in our website that I will show you at the end of the workshop, and you can see it. Hopefully in the next workshop, we cover those, okay? In generalized linear model part 2. Okay. But the purpose of this workshop is to understand basically how the generalized linear model works and what is the underneath, right? A little bit of the math, not much, and then it helps us to interpret the result much, much easier. And basically, if we see that the other kind of model is very similar. Okay, so now look at this. So let's say the average of my or estimated average of the outcome given a variable x is a value between 0 and 1, right? Then the mu here, it only, for example, covers from 0 to 1. But the linear function is, as we said, is from negative infinity to infinity. So how can I make this goes from 0 to 1 to negative infinity to infinity? I should put negative infinity, infinity here, so it's more clear. Okay, and any value in real numbers, right? Here you have all the positive number. It could be 1.2, it could be radical 2, right? It could be 3.555559, but it's a value that is positive. It doesn't have to be integer. I just show this as a line of numbers, right? So here from 0, 1, you can use this function, which we call odds function, to make this value from 0, 1 to go from 0 to infinity. As you see here, if I make the mu large and large and large, sorry, I repeat that. If I make the mu get closer to 1, the denominator get closer to very small number, closer to 0. So the whole thing goes to infinity. So by dividing by 1 minus mu, I made this mu as a transformation to be able to go from 0 to infinity. Now, when I have 0 to infinity, I can add another function on the top of the odds function, right? Is plus is not a right, is log in the parentheses, or usually in mathematics they show or. So log, so is a function of a function. Then this log function, the good thing about log is take any positive number and make it from negative infinity to infinity. So this kind of transformation that is used, like smart people came up with this transformation years ago, but this is not necessarily the only way you can transfer this. For example, there is a probit model, probit logistic regression with probit link. We call those link function. Okay, so those are the link function that gets this mu. Now, if you go backward, you can go from negative infinity to infinity, backward to 0 to 1, right? So you go to inverse this to go back to 0, 1. So I got this from Wikipedia page of GLM. It's not everything, but it's most of them. And in normal, it says link is identity. Look, this is just as it is. We call this identity link, right? We don't do any transformation. So basically normal, if the outcome is normal, already the mean could be negative infinity to infinity. So the link is identity. And the mu is x beta. This is the matrix format of what I wrote here. And there is exponential gamma, which I don't really know. There is a lot that, but you see, every single of these kind of generalized linear model, if you hear that, think about what is the link function, right? And then you can look at the link function and you understand, oh, this is very similar, right? It's just inverse and negative inverse. And there is inverse Gaussian, which is just inverse square of Gaussian. And Poisson, which is just a log, right? Poisson is just jumping from here to here. You only need log, right? So it's a log. And Bernoulli, which is our logistic regression, is this guy. The link is ln, which I showed you here. Because in Bernoulli, the outcome 0, 1 on average is probability. So we will see later. But that probability is something between 0, 1. So the outcome is not probability. The outcome is 0, 1. But the expected outcome is a value between 0 and 1, right? So for example, if you throw a coin, you expect to get 1 with probability 0.5, right? So that's a very simple example of that Bernoulli trial, right? And the link is this. And a binomial, very similar to Bernoulli. The only thing is binomial is many Bernoulli add together. So you flip a coin 10 times and then add the result together is binomial. If you, instead of head and tail, put 1 and 0, right? 1 for head, and then 0 for tail, and then add together, you get number of head, right? Exactly, very good question. Very good question. Somebody asked in the chat, the link function is different from normal, right? Normal had a plus epsilon, right? But these are not where the variation comes from. And you will see very soon, okay? Very soon. And there is like multinomial also is very similar. Now you see that they are not much different, right? And here you see the mean function, which is inverse of the link function. So this is backward from going from this way up. Okay. So two function, I said that we look at two function a little more, which is Bernoulli and Poisson. Now look at the odds before, like this. We want to really understand that link function. Basically, the first link function was taking a value from 0, 1 to 1, 0 to bigger than 0 to a positive number was odds function, right? But odds is something that people use in every day, especially gamblers. They use odds, right? So you heard about the odds. Odds is not probability. Basically, it's probability of success divided by probability of failure. So the example I use here, and then I use a very similar example to the regression model from the data we have, is probability of getting admitted to graduate school. On average, let's assume is 0.3, right? So if one random student from the population, and we don't know any information about that student, it's just a random student, probability of getting admitted to, if they apply to graduate the school, is 0.3. What is the odds of getting to a graduate school? Is just probability of success. We assume success is getting admitted. I don't know is that success or failure, but hopefully success, divided by 1 minus probability of success, which is probability of failure. Sometimes they use as Q, right? And it makes sense. So we get this value, right? 0.4 is a little bigger. Now, if you look at the odds of not getting admitted, you get 0.7 divided by 1 minus 0.7. So it's a value bigger than 1, right? So, you know, the odd can give you any value. As this value gets closer to 1, denominator gets smaller, and numerator gets closer to 1. So it basically goes to 1 divided by 0, which is infinity. But never gets negative, because numerator and denominator both are probability. One is probability of success, one is probability of failure. Okay, so that's for the odds. Now, let's look at this example and think about it for a second. So CNN analysts predict Los Angeles, when they were good, has odds of 9 to 1 to go to playoff. What is the probability of Los Angeles Lakers goes to playoff? Will go to playoff this season, I don't know. But this is how you calculate the probability from odds. So we are going to solve that equation for P. So we are going backwards. So P is equal to this times this, and P times 1, you get this, and P plus P times odds is odds. We takes, basically, yeah, somebody is writing here. So we takes basically, oops, sorry. Yeah, it's okay. You can clean it. If you want to write it here, you can. But if write for everybody, so. Yeah, so basically the way that we go from odds to probability is is basically odds divided by 1 plus odds, which is 9 divided by 9 plus 1, which is 0.9, right? So this is a very simple example, and you can see easily from odds, we can go back and calculate probability, right? And from probability, we can calculate odds. So another useful function was, as we see, log function, right? And let's see a little, you know, I want to show you a little math of this. And please bear with me if it's boring, I know, but we have to go over this to really understand the generalized linear model. So another function is exponential function and log function. So for example, for 10 to power 3 equal to 1000, then log of 1000 on base 10 is equal to 3, right? So that's how you define the log function, right? So log is basically inverse of exponentiate. And then we call that, we say, how we read it, we say the logarithm base 10 of 1000 is 3, right? Log based on 2 of 64 is 6, right? If that's true, then that means 2 to power 6 is 64. So we can go back and forth from exponent to logarithm. There is one particular base that is very interesting value, which is the Euler number or E number or natural number. And that is summation of 1 over n factorial from n equal to 0 to infinity. Basically, that value factorial means you multiply n by 1, n minus 1 by n minus 2 until you get 0. And that value is approximately 2.7. Okay. Now, for example, if e to power 6 is equal to a, then what is the log of e of a? So basically that value is equal to 6, right? So the answer is 6. Sometimes what I do is I take log from both sides, and because I know the properties of the log, I can just simply calculate, and log of e is 1, then I get 6. But there was more here. There are some rules in the log. There is one, when you have exponentiate, right? Exponentiate of x plus y, which this exponentiate means the e, right? E to the power x plus y. When we say exponentiate, that means e to the power that value. Like ln is basically log based on natural number. So since this is true, then you can write exponentiate, then you can write log of x times y equal to log of x plus log of y. Yes, recording will be sent after, but it takes some time to edit. Yeah. And then there is another rule. Basically, log of x divided by y is log of x times 1 over y, which is log of x plus log of 1 over y, which is actually log of x minus log of y. Okay, so that's for you. Sorry about that. Okay. Now, in part 2, we can start our logistic regression. Any question anybody has, please ask. Any questions so far? So we are going to use this log function and exponentiate function and also odds function, basically to be able to interpret the result of regression. Okay. So now, in logistic regression, in linear regression, basically, let's go back. We assume that the errors are distributed from normal distribution with mean 0 and variance square. Somebody asked where the variation comes in other regression model. And we will see now. We can say the outcome x given y given x has this distribution, and the variance of this outcome is sigma, right? But if the outcome is from, for example, Bernoulli distribution, that is not true. In fact, the Bernoulli distribution, the variance depends on the mean. Also, that's the same for Kant model, like Poisson model. The mean and variance are equal, so the mean and variance are not independent, right? So this mu is not independent. Sorry about that. Estimated from sigma. So let's look at those randomness, right? So before that, let's look at some distribution. This is the continuous random variable. In continuous random variable, every single value has a weight of possibility. Probability of x equal to, for example, 1 is 0, but probability of x between 2 here and 4 is the area under this curve. So we call this PDF of random variable, or probability distribution function, this function. Now, sometimes the variable is not continuous, and it gets a countable values, but by countable is, here it was non-countable maybe. But for example, you can get integer value only. If you flip a coin until you get the first head, number of times you need to flip could be 1, could be 2, could be 3, could be more. Although the probability is very small, but there is a chance, right? So this is the domain of the value that variable can get, which is positive or integer number, right? 1, 2, 3, and all the integer number, and not 0. Or for example, some of outcome from rolling 2 dice can be 2, 3, 4, up to 12, right? Or number of patients a hospital admitted based on their COVID, or they get hospitalized based on COVID. So that also is a discrete random variable, right? It's countable. Not necessarily count, but is discrete. A categorical variable with 3 levels also is discrete, because you can get, for example, green, yellow, and blue outcome, right? So that also is a discrete random variable. Most popular discrete random variable is a Bernoulli. Bernoulli can get only value 0 and 1, and this is the for discrete random variable, you have a probability for a fixed number. So you have probability for 1. Probability is not 0. I think that's it for this slide. Yeah. Now look at the Bernoulli distribution. The outcome of logistic regression, as we saw, is 0, 1, right? So Bernoulli distribution is a random variable that the outcome is either 0 and 1 based on some probability. The mean of Bernoulli distribution, which is expected value of the outcome, can be calculated by 0 times 1 minus p plus 1 times p, which is p. So now you see that there is a mean, there is a variation. So that variation that you were looking for, somebody asked, is come from this distribution function. So you don't really need that epsilon, right? For example, for here, the variation comes from the sampling distribution of the outcome. So the variance of Bernoulli can be calculated using this formula, and which is not very important how you know that or not, but is p times 1 minus p, which depends on the p. So again, this p was the expected outcome, right? Kind of, you see that now the expected outcome is not always equal. This is a probability mass function of Bernoulli with probability of success equal to 0.3, right? 0.3, this is all the probability that value 1 can get and 0 can get, right? And there is no x value. Probably you don't need to put this value. It's just 1 and 0 and 1. So this part is optional, so I'm not going to, we don't really have time to go over this. And it's just going over binomial distribution, which is extended of a Bernoulli trial. Now, let's go and start with our first generalized linear model, which is the logistic regression. So in logistic regression, we have the outcome that is only has value 0 and 1. The data that we are using in this example is the data of a student getting admitted or not admitted based on some scores they have, based on their GPA and GRE and the rank of a school that they are applying for. So there is 3 predictors. You can copy paste data from here. Also, this code exists in the code file. And the file name is binary and is just admission database, right? 4 random variable. And the outcome of the regression that we want to run is what is the effect of this GRE and GPA score and the rank on the outcome, on the probability of admission, basically. So this part also is optional. I explain a little bit about the relationship here and what if we run it as a linear model. So we can skip that without any lose of relevancy to this workshop. So I'm jumping to this part that is actual logistic regression. The code for this part that is also in the code, but I made it as a command so you don't have to be run it. If you like, you can uncommand it and run it. Now, let's go back to logistic regression. In the logistic regression, we had this formula, right? And we had this link function, which was log of odds given some predictor variable, right? Now we can rewrite that. Let's go back to the actual mean, right? So this value, as we saw before, it could get any value from negative infinity to infinity. So that works. The linear model works there, right? Let's go back a little bit to that slide. I think, yeah, here. So as you see here, this function makes a value between 0 and 1 and transfer it to a value between negative infinity and infinity and positive infinity. Now we can go back to the value between 0 and 1. Okay. So that's what we are doing here. So we can rewrite that, exponentiate both sides. So this is going to be odd is equal to exponentiate of beta 0 plus beta 1, or e to the power beta 0 plus beta 1, or this linear relationship or linear function, right? And from here, as we saw in the Lakers example, we can solve that to get the probability. Or another way they write this formula is this way. So basically what they do is they multiply numerator and denominator by e to the power minus that linear function. So that part is going away, is going to be 1, and denominator is going to be 1 plus e to the minus. E to the minus comes here, and you can exchange them, right? So this is two way to write this formula. Probably you, if any logistic regression board you open, you will see these formulas. So that comes from the transformation back from odds to probability. As you notice here, we don't need sigma, right? The P gives or the P, the probability mass function, gives us the variability, right? The randomness. The randomness comes from there, so we don't have any E. But you know, sometimes in some model, maybe people wants to add another extra variation, right? But you can't do that, right? But here we don't need it. So did I answer that question? Any question? Let me stop here. Sure. So any question? Anybody have a question? Okay, we continue and hopefully we finish quick. So in R, we use a function GLM to run generalized linear model. So basically, using this and that probability function and that probability mass function, we will be able to estimate the parameter of the model, right? I'm not going over that part. I did a little bit in the Poisson part, but and if you look at the binomial model, you will see the connection that how we can use likelihood function to estimate that. And they use maximum likelihood, but is not is a lot and is not relevant to our workshop. And we can just without lose of any idea of the workshop, we can skip that part. So now R runs a GLM function to get to estimate that model. Now in R, in GLM function, there is one part. right? Generalized linear model. The formula is the same, right? The linear part. This part is the same as the linear function. But what is added is that family first, which is telling you what kind of distribution is the outcome and what kind of link you like to use. So you can use, the binomial family, but not Logit link, any different kind of link. The link, again, is transferring a value between 0, 1 to a value between negative infinity to infinity. So, for example, in probit, it use inverse of normal 0, 1 in the standard normal as that function. So it looks very complicated, but somehow it works very well, right? So, but anyhow, the way that GLM runs and gets your estimation is through iterative method, is through a numerical method. So complication of those formula, the computer doesn't care, right? When it doesn't have to solve the problem, is not the linear algebra course or algebra course for the computer, right? So it runs through that. But the LM model, although run the computation and numeric methods, but there is a mathematical solution for LM or OLS. But as a side note here. So after you run the model, you get the estimated intercept and a slope. This intercept and a slope are these betas, right? So is here is a linear predictors, right? And therefore we call it is they are in the metric of Logit, right? So they need to go back to get to the metric of, for example, odds, right? Or you don't have to, right? Now let's see. So we estimate these and what those means now, right? In linear model, we say for 1 unit increase in the predictor, the outcome is expected to increase by this much, right? Now here, we can say the same thing. We can say for 1 unit increase of the predictors, look at this one, right? For 1 unit increase of GRE, the outcome increases by this much, by 0.00382, but that's not the mean of the outcome. That's log of odds of admit increases by this much, right? Log of odds of admit. Now, if you write that, some people write this in their paper and it's fine, but sometimes it depends on your audience. You want to make it in very simple English language, right? So they really understand what's going on, what that value means, really, right? Okay. So I said it's not very useful. It's not easy to understand, but it is still useful. At least we have these p-values, right? This is not correct. The p-value, this can see this positive relationship is not very likely by chance, given that you assume there is no relationship between GRE and the admission, right? So if you assume there is no relationship between GRE and admission, then the chance of getting this effect or something more than this effect is basically this much. That's the p-value. Okay, now We can exponentiate the slope, right? If we exponentiate the slope, we get the odds of admission for somebody with GRE equal to 0, right? If we exponentiate both sides, if GRE is 0, then it's going to be exponentiate of this value, and exponentiate of this value is this, right? 0.05. And then we can transform that to probability to get the probability of admission for someone with GRE score equal to 0. So that's if their GRE is 0, that's the probability of getting admitted. It's 5%, right? It's not very good. Now, what about a slope? What if we exponentiate that value? Now, let's look at this example. Let's do the same thing that we did with the linear model. For 1 unit extra GRE, let's see what happened to the outcome. If we have the odds of, for example, somebody has a GRE score 500, right? And then we can use that formula and exponentiate both sides and get odds of 500 equal to e to the minus this linear prediction, right? If their GRE score increases by 1 unit, then their score will be 501. Still, we can get their odds, right? Now, we are not calculating that. Wait a second. If I divide these two, right, I divide this one by this one, odds of 501 divided by odds of 500 is going to be these two. And then we can simplify that, right? Everything will cancel. The part that involved beta 0 will cancel, which is a slope. The part that involved that 500, it cancel. So I end up with the part that only involved the slope. And that is basically the ratio of the odds. So, or odds ratio, right? So if you exponentiate that slope, then you get the odds ratio of the outcome. And this odds ratio is constant no matter what GRE score is, right? Again, the odds ratio is ratio of the odds from some value to the another value. So it doesn't matter what value here it is, that still is odds ratio. And that odds ratio doesn't depend on the value you start with, the 500. Depends on that 1 because this is 1 right here. I multiply that by 1. So we can do this. We can exponentiate that slope. We get 1.003588. And that means for every 1 unit increase on the GRE score, we expected the odds of getting admitted to graduate school increases by 3%. You see, this is different than before. Before we said decreases by this much, but now we say, I'm sorry, increases by 0.3%, right? How I get that value? Basically, this value increases from 1 by 3%, right? Or 0.3588, but approximately, right? Okay. This GRE is an old GRE score. Right now, GRE point increments by 1 point, but the old time GRE score incremented by 10 points. So there is no 1 point extra GRE, right? Now, what if we wanted to see if someone improved their GRE by 50 units, how their outcome increases, right? So that makes sense, right? 50 units, if I increase my GRE, what is the chance of admitting, or what is the odds of admitting will be different, right? So let's do that, right? So odds of 550 divided by odds of 500 is going to be this, is going to be cancel everything. 50 is going to be here, and this is going to be e to the this value to the power 50, or is going to be 50 times the slope and then exponential, right? So there is two ways to calculate that, basically. But it's multiplicative, right? It's not additive. So the odd is basically the logistic regression. The effect is multiplicative increase of the odds ratio, right? So if we calculate that, we get 1.196 that, and this is basically is 20% increase. So the odds increases by 20% on average if somebody increases their GRE by 50 points. Okay, any question? Any question? Question. Is it me doing the annotate? No. Let me see. I wanted to, okay. So there is no question. So I'm going to give you one actually exercise so you can do some analysis. The result is not here, so you have to do it. So the question is this. Logistic regression model of admin by GPA. So run the logistic regression of admission by GPA using the same data. You can copy the data from here in R. There is no package you need to download for running this exercise, basically. You can just run this code, you get my data, the function is GLM, you can copy paste and change it to GPA score, and then calculate the exponentiate of the slope and interpret the result, and then answer this question. If someone increases their GPA by 0.20, how the expected odds of their admission change? Okay, so that is as exercise. And let me see, it's 2:34. And how about we get also a break and come back at 2:40? Okay, is that okay if we have a little break until you work on this exercise and get the result? Good. So, and meanwhile, I'm getting a water. Okay. So basically, you run this, run the same model, calculate the odds, and then calculate the answer this question. And think about the way you interpret the result. Think about how we interpret the p-value, or should we, how we report it, things like that. And yeah, that would be a good example. Okay, I'm coming back in 5 minutes from now. GPA increases by 0.2. Because, you can do you're welcome. You can do GPA increase by 1 point, but, somebody from 3 to 4. But that's how I made it like this. So you can also get some more realistic result. Okay, now let's do that in R. Okay, so I'm going to, do I share the whole screen? Let me stop share and share again the whole thing. I can go to R. Okay. This is a small. Let me go to my R option and make it a little bigger. Okay, is that good, big enough so everybody can see it? Yeah. Okay, do you see my R? Okay, so the exercise was here, right? Okay, so we read the data, and in R, I use usually Control Enter and run that code. I just need to put somewhere here. If I select like this, it doesn't work well. So you can just put it somewhere and run it like here. And then it reads the data. So this is the data set. So you can see GRE, GPA, admin, rank. And now I can run this GLM model too. I call it, so you can call it anything you like. And then GLM was the function, right? My outcome was admit. And then tilde. And it was GPA. And R is case sensitive. So if you make GPA as capital, it doesn't work. Data is equal to my data. Now, there is a family, right? Let's look at GLM here. Now we are here. Let's look at GLM help, right? Question mark GLM gives us the GLM help. Well. Can I make this larger? I cannot make it larger, but hopefully you can see. You can just do it for your computer and see it. So there is a formula family. Gaussian is the default, right? Gaussian means normal. And then there is a link function, right? Family, and here somewhere you should say like link function. And then you click off on the family, you will see, oh, here, binomial link, right? Gaussian link identity. These are the default. Everything here is from, is default, right? So gamma inverse, link is inverse. Inverse Gaussian is link inverse. We saw that, right? We saw this. Poisson, link log, and so on and so forth, right? So you can, this is how you can read the help file in R. It's very helpful. And then there are references there. There are examples on the very end. So you can run different type of GLM model, ANOVA GNM, things like that are here. And you can, there is a, these two people are the people who basically, this one especially is one of the co-author of the first, very first, I think, paper in Generalized linear model. And these two are basically very good. Then this book is very technical. And this book is basically referenced in all the paper they use Generalized linear model. And yeah, so this is for GLM in R, and then there's a lot, and there is weight, things like that, and yeah. Another thing that we will use here is offset, right? Very cool, right? So, okay. Now, we have to define the family, what kind of distribution? Family. And the good thing about RStudio is already give you the options. Equal to, and then I put it to the second line so you can off the, and the family for logistic is binomial, right? Not binomial test, binomial. And then in the parentheses, you see here it comes, link is Logit, link is equal to, and the option should be in the quotation. Logit. Logit is that Logit function, right? So hopefully that runs fine. Yeah, I got this list, right? If I do class of GLM dot model dot two is GLM and LM, right? So it's basically very similar. LM gives you LM, but GLM also is very similar to LM. It's the same class, so everything you can run over LM function, you can pretty much run for GLM model. And then you get the result by like a summary, right? By GLM dot model dot two. It was my model two, right? And then you do that, and then you get the result, right? So you get the, this is deviance residuals. In LM, you get the residuals. This is called deviance residuals, and there is a Poisson residuals, and we are not much going over those. It's more technical, but it's good to know some. I put some calculation there, but yeah. So, and this is like model fit basically, and you get the p-value. Now let's see how we can interpret that. As we said, this value is in the Logit metric, right? So for every one extra GPA, the log of odds increases by 0.5. Let's see what that means if we do exponentiate. So when we do exponentiate this value, you get 2.86, right? Now, again, we don't have to copy paste it. We can exponentiate from extracting this summary. The summary coefficient of summary gives you the coefficients. Right, you see the coefficient, and the estimate is here. So this is basically kind of like a data frame. So what I do is I say, and I want this GPA, right? So is the second row, first column, right? So it's second row, first column gives me that value, right? So you can extract it exactly if you want this way. And exponentiate value of this was 2.86, right? So now there is one way that I used before, and then I subtracted 1, and I got 1.86, and that means if somebody's GPA increases by 1 unit, then the expected odds of outcome or odds of admission increases by 186%, right? You know, it's very not nice to use like 186 in the paper. So instead, we can say if somebody's GPA increases by 1 unit, their odds of outcome, odds of admission increases by a factor of 2.86. That's another way to interpret the result. So by a factor of 2 increases by this factor, multiply by this, right? So you can use that also on average, right? Okay. Now I ask, what if the GPA increases by 0.2? Then one way is to do this. Exponentiate these times 0.2, right? And then you get by 23%, which makes sense, right? Now, the odds of, not probability, be careful, right? The odds increases. We cannot make any inference here now about the probability unless we want to calculate the predicted probability for a particular person. Okay, so we cannot say their probability of getting accepted increases by 20. That's wrong. Okay, so yeah, or we could use the way I did it before, which was exponentiate of this to the power 2, which gives the exactly the same result. Okay, so any question? All right. So are you ready to go to more? Okay. So now what I do here is very easily we can add many variables, a loss of variable, right? Depends on how many samples, how stable is our estimation. Exactly the same as linear model. So in here, I add GRE and GPA, both together. So I want to see what is this model. So model GLM, model 2, model 3 is GLM admit predicted by GRE and GPA. Still, family binomial link is Logit. I don't have to put this here because by default is Logit, right? But I can change it to different type of link that comes with that family. Okay. So when I do that, I get 2 slope, right? One for GRE, one for GPA, one intercept, right? Now you see the slopes are kind of losing their significance, right? Or they eat each other's effect, right? Because they are very correlated. If somebody's GRE is high, their GPA also is high. So, and then I get the coefficient with this, I get the coef, I get the standard error, I get the Z value. Now you see this is Z value is interesting, it's not T. So generalized linear model has different kind of assumption. It's not the same as linear model. So there is no like same asymptotic distribution makes sense here. So, but however, because if we use maximum likelihood estimation, the parameter estimated asymptotically distributed as normally distribution, as a normal distribution. Okay, so this is in general true for any type of maximum likelihood. This is true. So that's why they use this z-value. And then I can get expected value of those all coefficients, right? GRE and GPA. And now the way we interpret this model is a little different. Now we can say the odds of getting admitted on average increases by a factor of 2.12 or 2.13 for 1 unit improvement of GPA given GRE score is constant. So basically, if we can randomly find two people that one person GPA is one more than the other, and they both have same GRE score, the odds of the person with the GPA higher, 1 unit higher, on average, we expect to be by a factor of 2.12 more, or the odds is about 2 times more. Make sense? So this is for keeping the other variable constant when you don't have interaction. Now, let's see if we have the same model and having interaction between GRE and GPA, right? This is the model that we have GRE and GPA, but we interact GRE and GPA. If we do that, then we have the interaction. So in R, if you want to include interaction, you just need to multiply those variables by each other. So the main effect of those variables and interaction will be there in the model form. Let's see the family binomial, and this is my model 4, right? Now I run this model, and the interaction is not much, but it's something, right? So you want to see if how you can interpret that. Now, again, if you want to see the overall model, you can run this model, run a model with intercept only, and see overall this model is significant or not using likelihood ratio. I haven't done it here, so but that's how you do it. I thought it gives you already here. It doesn't. Anyhow, so I get the coefficients again. This confidence function gives you the confidence interval for the coefficients. Sorry. So I will talk about that, how they calculate it. Basically, what they do is, let me tell you, is that they have the estimated value, they have the standard error of this estimated, they have the z-value, they calculate plus minus 1.96 of that times a standard error of that estimated value. And you can, oh, this is the let me see. Minus this. Sorry about that. This gives you the confidence interval for the Logit metric, right? So there is no transformation, anything. If you want to transform it, you have to exponentiate both sides. And the reason that, okay, so this is what I wanted to say. The reason we cannot transform this first and transfer a standard error is that we don't know what is the distribution of going back from beta to exponentiate of the beta. It's not going to be normal anymore. So you cannot use the Z distribution. But when is the metric is beta, which is the log of odds, then you, the distribution is normally asymptotically. Okay, so anyway, yeah. So I calculated that. I calculate the now if I want to see what that means in linear regression, this interaction was additional, right? Still, if you want to interpret this as the log odds, this interaction is the additional to this value, GPA. So for 1 unit increase of GPA, there is additional increase of GPA for a person times for a person with GRE score, for example, 500, right? So you can calculate that simple effect for a given value of GRE. You can calculate the simple effect of GPA, right, this way. But however, in here is a little different, right? So again, it's like kind of multiplicating. So first you can multiply by 500 that interaction from here, and then you can find the exponentiate value, and you get this simple effect. Another way is to the power 500. So that's another way to get that value, that simple effect. Basically, the simple effect is the effect of GPA. Is that for GPA? Yes. Is the effect of GPA for one unit increase of GPA on the outcome for somebody with the GRE score of 500. Okay, any question on this? But this is basically additional here, but multiplicational when you are using the exponentiated value. So if I exponentiate that values, right, then I have to the power 500 to get that simple effect. Okay, and it explains here a little bit. Now, for logistic regression, I'm pretty done, but this is not over. So there is a lot more about logistic regression that you might face. So there is diagnostics of logistic regression. There is sometimes the problem of separation. So you remember logistic regression is kind of like a chi-square test. In chi-square, 2 by 2, basically, I tell you that logistic regression, when you have a variable that is dichotomous as a predictor, and the outcome is also dichotomous, is the same as the chi-square test. Simply the same model, right? So a little more, but very similar model, okay? In the chi-square, when each cell, expected value of each cell is very small, and you say the rules of 5, remember that? We said, okay, we have to do exact chi-square. Same for logistic regression. Sometimes you cannot even estimate, right? You cannot estimate. And they use different type of models. So if you click on this link, you go to one of our website. This page is basically for explain that issue and in different softwares. In R is there, in SAS, in this data, and talk about the problem of quasi or complete separation. And you can read that if you like to. You see it's one course itself, right? So in R, there is a package and there is a method that panelize method that you can use to estimate those kind of methods. So there is a type of regression is Firth regression, Firth regression. So logistic. Yeah, in R you can see there is a package for that is Firth Logis TF. That package you can use to solve that problem. Okay. And also for logistic regression diagnostics, you can look at this page, which is in a data, but you get the idea of what kind of diagnostics we need to test and things like that. Pretty much when your predictor variable is not continuous, there is not much of the diagnostics. Everything works fine. Okay. If the predictor value continues, you need to somehow test for that linearity, because that relationship we assume is linear, but we're not sure. So might change, right? So that's the thing that explained here also. Any question? If you want, you can unmute yourself and ask question. Okay. Now, another type of the outcome that is not always from -infinity to infinity is a count data. So there is some more formula here, but I don't go over all the detail. You can read it by yourself if you are interested. It doesn't change the idea that we get is the same. So there is kind of PMF, probability mass function, and there is the mu, which is the mean value. Sometimes they use lambda for that. And yeah, and then here I talk about how binomial model converges to a Poisson distribution. So Poisson is kind of like count data. So you get values 0, 1, 2, 3, right? For example, number of people that get admitted to hospital having COVID, right? It could be 0, could be 1, could be 2, and so on and so forth, right? Or number of, one good example that is very a standard example of Poisson is in the water, in 1 milligram of water, or I'm sorry, milliliter, or 1 gallon of water from a lake, how many plankton is there? So this kind of count is Poisson, right? So as you see in the Poisson, I had only one parameter, right? One parameter is mu. And here is e to the minus mu, mu and y is very close, but this is y, this is mu. So one example that is very simple example of Poisson that I made up is number of accidents per day in Freeway 405 between Santa Monica and Wilshire Boulevard in a sunny day. So there is no rain, it's sunny day. What is the accident? You know, we assume that the rate or on average number of accident is 2. It could be like 2.5. We don't know, right? But let's assume it's 2, right? This is the model that we made up, and we can just create that parameter. Using probability mass function, we get the probability for each value, right? For mu equal to 2, you calculate probability of 1, right? This is the outcome. For different mu, you can get the probability of outcome, probability of 0, probability of 1, probability of 2. So, but your outcome could be any number, right? Based on these probabilities. And that's a randomness part of the Poisson model. And you can plot this. The probability goes for all the numbers. This number goes to infinity, but usually the probability stops in Poisson because it's skewed here, somewhere here. Even when mu is 2, almost when we want to calculate probability of y, the value is almost 0. Okay. Very close to binomial, but not exactly. In binomial, we didn't have unlimited value of number of success out of n try. We had at most n success. But here, no. You can have as many accidents as you like, assuming there is no, you know, at very same level, there is a lot of accidents can happen, things like that. But there are assumptions. But yeah. So in R, you can use R POIS, DPOIS to get either random sample from a Poisson distribution, or you can calculate a probability mass function from a Poisson distribution. And basically is if you want to do normal random sampling, you do R norm, right? You do R norm here. I put in the chat, right? For example, 1. You create one random sample from normal 0, 1. In Poisson is R POIS. And here I calculated distribution probability or probability mass function for lambda 5.5. So again, I need to use that K so it doesn't advance. Okay. So this was when mu was 2. Now assume for a rainy day, the rate of accident is 5.5 accident per day, right? So again, we want to really understand that Poisson outcome to go back to Poisson distribution. So then you can calculate probability of each of the outcome, right? And it's a little different than this one. So this one for a probability of 0 was higher. Here the probability of 0 is lower, right? Okay. As rate goes up, this is going to be more like a bell shape, by the way. We can calculate the ratio of the rate. Rate in Poisson is exactly the same as the mean for normal, right? Is on average how many accidents, on average how many counts. We can say rate, so per day. Then rate per 2 days is twice, right? It's a little different because you can have 2 days, number of accidents, right? Uh, in normal, you cannot have something like that, right? So height of somebody is 6 foot. Height of two person together, I don't know, it maybe like added. But anyway, the rate makes sense to have per day, per 2 day, per 30 days, per half a day, right? That's why we can use the mean as the rate. And that is rate of the count. So this rate, ratio of rate can be also say, we can say that the mean of accident per day in rainy day is 2.75 times more than accident per day in a sunny day, right? So that's how we can see this day comparing to rate. Now, here I generate example. I generate some distribution using these probabilities, basically. And basically, I tried for myself to create some sort of Poisson distribution, but I wanted to add some zeros, right? And I wanted to see how that distribution will be different. So in this sample that I created is not exactly Poisson, but I use this probability to draw sample from 0 to 8 number of accidents. The mean and variance is almost the same, right? As it should be in Poisson. So in Poisson, the mean and variance is the same. So this is just kind of approximate outcome from a Poisson distribution, right? But if I add a lot of zero and then I calculate mean and variance, then you can see the mean and variance are not equal, right? So again, one thing, the variance depends on the mean, so it's not independent in like in linear model. But another thing is that in Poisson, mean and variance are equal, right? Or almost equal if you calculate the sample mean and sample variance. When it's not here, the data is pretty much very skewed, right? This in quant data calls overdispersion. So data are overdispersed for Poisson model. That's what overdispersion means. So if I want to run Poisson model, somehow I have to calculate that extra variation. So somebody asked where the variation comes from, right? One part, the variation comes from the distribution function here, right, that we have based on this probability mass function, but we cannot capture sometimes all the variance. So we have to add a little more variance. So that we call overdispersion. And that's how Poisson extended to negative binomial. Or you don't have to go to negative binomial, but you know, is Poisson here, negative binomial is somehow more extreme, and there you can adjust, you have to adjust for this over dispersion. So that was the idea I wanted to talk about this demonstration. So now I generate 1000. You see, even if you randomly generate from actual Poisson distribution, not exactly the mean and variance going to be equal. So if the mean and variance are a little different, there is no overdispersion, right? This is just a sampling variation on difference. So, yeah. Okay. So I can do the histogram. Histogram is very similar to that distribution function that we did. This is coming from sample that before was the actual. And there is another thing in Poisson. As I said about the rate, sometimes you collect the data not per day, per like 2 days, right? Number of accident in 2 days, or number of accident in a month, or number of accidents in 2 months, right? So if you want to calculate number of accidents in 1 month, in a sunny day, in every day in that month, then on average, that would be 60 accidents per month if there is no rain in that month, right? So that can be that formula. The formula for that, it only changed by this t, but the mu is the same mu, right? So the distribution will not change much. The only part that changes this t times mu, right? But the mu is the mu. And this t is exposure in a linear in a Poisson model. And we can use that exposure if we have the data that is collected for different units of time, or in different area, or in different volume of water, number of planktons, right? So that is very helpful. Sometimes you want to compare, for example, China to United States to Andorra, I don't know, like Italy, and each country have different populations. So you somehow you want to adjust for that, right? So this is how you adjust. We call that exposure in the Poisson distribution. Right? But you can see it here, and later we will see in the actual model. So Kant data is basically, going back, is the observation that is only gets non-negative integer value. The count can range from 0 to undetermined value, but usually is not very large value. The probability of getting very, very large value is sometimes very small, right? Most of the time it's skewed. The type of count data is the count of item or event occurring within a period of time, right? Or number of accidents. And number of events occurring in a given geographical area, right? Or a number of people having a particular disease. That's why it's very useful to be able to estimate these models more accurately than linear models. Yeah, there is some examples. Number of people died in a hospital within 48 hours. Maybe in some hospital, you don't have 48 hours, you have like 24 hours. Those are kind of exposure you need to adjust for, and things like that. Okay. Now, here is the review of what we said again. In regression model can be run using the linear model, right? But the problem is that you might get a negative value as expected outcome, but expected count cannot be negative, right? Another problem is that the outcome in the count model usually always, every time, almost always, it depends on the expected outcome itself. The variance of the response depends on expected response. In the Poisson is exactly the same, right? So it is not constant for all the value of the outcome. So that's a big issue. Again, I said normality is not big issue. This one is really big issue because then your standard error of parameter estimated is not going to be valid. So that's why we prefer to use this type of models. Again, Poisson is a standard. So usually we start with Poisson. Some people prefer to start with negative binomial for some reasons that we talked about it before, which is the overdispersion. So they want to estimate that overdispersion using negative binomial. And if that overdispersion is basically the ratio of those variants, or not exactly, is in a vague definition, you can see it that way. If, or in some formulation is 0, then Poisson is fine, right? Or is close to 0. But it depends on how we define that overdispersion. So again, think about overdispersion as extra variation that the model cannot estimate or is not appropriate to estimate that. So you can write the formula for the count outcome. Again, going back to that transformation that we go from 0, 1 to 0 to infinity, we use log from 0 to infinity to get to negative infinity to infinity. So this is a little easier, right? There is no odd, just log of mu outcome can be written as a linear function. So the link is log in Poisson, right? That's all you need to transfer a negative infinity, a positive number to negative, or inverse of the log. You can go back from negative infinity to infinity to the mean of response. So this is the mean of response. This is the mean function. This is the link function. Okay. So we can write this Poisson regression model as this. This is the probability of each outcome given x and those betas. You can write it this way. I'm not going to go over this in very detail, but I basically created these two plots for you to be able to somehow see the difference between Poisson and a linear model. In Poisson, for each given, so here is a given outcome, right? For even x, you get the given outcome. The given outcome is usually in the y-axis. So that y-axis is the mean value or average value or lambda or the mu or expected y given x, right? This x is minus 2.5. So the mean is somewhere here. The rest variation is because of the Poisson probability mass function, right? So you can see the Poisson model for any given value, you have the mean and then you have, but this variation, you see, it depends on the mean value itself. This plot is actually, I generate the data artificially and run a Poisson model, and then I try to estimate that model. So this data is exactly Poisson, okay? And you see that this is this, but the link function also is helpful because it's kind of like make this goes from this linear, if we do identity link, right? We could get the expected negative value, but we can make it like a positive, right? So you see x goes from negative value, could get negative value. expected y is always positive. There is no way to get the negative. So that's another kind of advantage of using the link. Right? You see, it's not linear, but the log of this is linear. Right? Log of these functions. In contrast, the linear model, it likes this. So for every given value, you get a normal distribution for the error. And that error has these errors. Now here, the error doesn't come from that epsilon, right? You don't have to have that. But here, the error comes from epsilon. It added, so it's mu plus epsilon, right? And then the variance of y is equal to variance of that epsilon, right? This is the linear and OLS model, right? Now you can see the difference between these two, generalized model and the linear model more clearly. Any question? No question? Okay. So let's go back to that artificial example as the Poisson regression of the accidents. So we can basically generate artificially two sets of data, one for sunny day, one from rainy day, and then put them together, define a sunny, rainy variable as x, right? 0 means is a sunny day, and 1 means is a rainy day, okay? So then I can run this data that I generated. You see here, I don't have data equal to data, right? Because these two is already generated as a two object, as two vector in my working directory. So it exists there. So I can just call them. I don't have to make a data set, but I could. And then you run this accident model and get the result. Now, look at the result. This estimated value, do you know what is the metric of these coefficients? Think about the link function. The link function here was log, right? So the metric is log. In Logistic, the metric was Logit, right? Log of odds. Now, we can still interpret that going from a rainy day a sunny day to a rainy day, right? So the rate of log of rate of, okay, no, let me clear that. Log of rate of rainy day minus log of, so the change of log of rate decreases by 0. Actually, no, increases, sorry about that, sorry. Increases by 0.95 for going from sunny day to rainy day. So this is basically again, let me correct myself. You have to be careful because my outcome was my predictor was a categorical variable, was 0, 1. The reference group is this, right? So the reference group was a sunny day. So the log of rate of sunny day is this value. The log of rate of accident, expected log of rate of accident, is 0.95 95 more than log of rate of sunny day. So that's how you can interpret it as log of rate. Now, if I calculate the rate of sunny and rainy by hand, I get this value. If I get the expected value of the log, I get the mu, because expected and log are inverse of sunny is yes, coded at 0. Yes, sunny was 0. So this is the sunny, which is I actually put it here, and the rainy was 1. Yes, that's correct. Now the rate of sunny day is 2.3, which is close to 2 that we start with, and the change of the rate, the fraction of the rate is 2.58, which was what? 5 divided by 2, it was 2.5. So it's very close, right? Now we can calculate that only by hand using this, right? If we have actually a categorical and the outcome, and there is a balance, then you can just calculate that by hand. But that not always the model can get very complicated. So this is one example. Is kind of the example is very simple, but it makes you think a little more, right? So I explained that how to interpret the outcome in another example, a little more, so you can see. And by the way, the good thing about the Kant model is all of them, when you want to, in all of these models, when you want to interpret the result, the way you interpret it is very similar. So if you learn Poisson and how that works for binomial, for negative binomial, that works for any type of the log transformation. And there is a lot of log link in different statistical methods. So it's very good actually exercise. So this part is optional. I put the log likelihood, and I talk about how do we maximize the log likelihood to estimate. But this is one example that is based on the data. There is a package count in R, by the way, right? So there is a lot of other functions you can use using this package that related to the count regression model or count data. In this package, there is a data set that is about the German National Health Registry from 1984. The source of this is from 1984 to 1988, but this data set is RWM 1984, is only the data from that particular year, is a longitudinal data. So I use this data for count regression, and throughout this, there is other problems that negative binomial, but which is we don't have time to cover, but the code is there. So use that to call that. First, you need to install that package, of course, and then data in the quotation. If you put the name of the data will be in your workspace. And you can see the data. It's doctor visit, hospital visit for each people. Age of person, out of work, they are either married, they have kids and education and different. But what they're interested is to see how the number of hospital visits for each patient changes, maybe in a year, maybe in a month. I don't know exactly. You need to read that help file of this, probably explained there, but it doesn't really matter. Number of hospital visits for whether or not they are out of work, right? So if they're working, do they, because they probably they have insurance, they have more visits, something like that. I don't know exactly what you have to read that paper, but that's what we do. We run the Poisson model using age and out of work as predictors because we want to get that number of visits for controlling for the age, right? That is very important because if somebody is 30 years old, 26 years old, probably they visit hospital, doctor visit. Oh, I want to do the doctor visit. The doctor visit is going to be apparently for this person was 9 anyway. So probably is less, right? But we'll see. So you can see the summary of the data, and then you can to be able, remember before we didn't interpret the intercept, right? Now, if we want to interpret the intercept, we center the age. If you center the predictor variable, then the intercept will be the number of doctor visits when they are at their average age. So that's a good advantage to centering. So we can center that age first in the data and then run the regression using doctor visit, out of work, and centered age. And family is Poisson. You see, this part is only part is changed, right? Again, we use that, but the link is log, is not Logit, and the family is Poisson, right? Which we saw in the rainy, sunny accident data. We run this model, we get the summary, and there is a lots of things. Again, deviance residuals here, same as, so there is something there that dispersion parameter for Poisson family taken to be 1. That means there is no over dispersion assumed for this one. So we fix that and we don't estimate another over dispersion parameter. Okay. So, and that affects the number of degrees of freedom of the residual deviance. Okay. So, by the way, null deviance is the, let me see sample size. I'm giving sample size, but yeah, I should see that sample size. But null deviance is the deviance when you run the Poisson model for intercept only model. And the residual deviance is when you run model with these predictors. And it show you these two. Yeah. Okay. Deviance means basically it's some sort of the same, similar to that residual, right? In fact, the Pearson deviance is exactly the same as the way we calculate the residual. The predicted outcome minus the observed outcome. So now let's interpret that coefficient in this term the same way that we did before. So for difference out of work at work, right? So that value log of r, log of mean has a linear relationship. So we can use this formula, and this is beta 0. I didn't put the value actually, but I could put this value, but I want to show you how that works. So this is the linear prediction for somebody with some age at work, right? Equal to 1. And minus somebody is not at work with the same age, right? Let's say with the same age, keeping the age constant. If we do that, then everything cancel, and that B1 will be left, right? Because this is at work equal to 1 is 1 minus 0, right? So you get this coefficient. This coefficient is log of mean of at work minus log of mean for not at work. If we use that log formula that we saw before, property, we get log of mu1 divided by mu0, right? So we saw that we can do this. These two are equal in the log. And now if we exponentiate both sides, we get ratio of the means, or rate ratio, right? Or some people call it incident rate ratio, right? Incident rate ratio, right? So if I exponentiate that, the incident rate ratio for somebody is at work increases by 50% compared to somebody is not at work on average, given they have the same age. Okay, this is how you can interpret that, right? It is better, it's much better than interpreted in the log metric. Makes sense? So it's 50% is more. Again, I use that -1, but when it's more than 2, I don't like really like 150% or 1000%. Then I use the then I can say also this. I can say the odds of I'm sorry, not the odds. Their incident rate ratio, or their on average, the rate of doctor visit for somebody at work compared to somebody is not at work increases by a factor of 1.5037 for keeping the age constant, right? So if you randomly sample to 30%, 30 years old person from the population, one is at work, one is not at work, you expect their rate of doctor visit to be in a factor of 1.5 more for somebody at work. Question? This is very important. Actually, it's very get very confusing, but when you learn it one time, then you can extend it to all kind of model. It's very interesting. So this part I put as optional. So why you are still exponentiating if this is a log link? Yes, because the log link, I need to, okay, let's go back to here. Very good question, actually. In odds, when I exponentiate, I got the odds ratio, right? I didn't get a probability ratio, right? And unfortunately, from odds ratio, you cannot get probability ratio. right? There is no way to calculate that unless you have two exact value, right? Okay, this is one thing. Now, second. In here, also, I have linked log. So I need to go back to the mean ratio, right? So I had to take the exponentiate of these two sides, then exponentiate of this coefficient is the ratio of the mean. Did I answer your question? Okay, good. So remember, in the logistic, we did two steps. First, from 0 to 1, we went to positive, and then from positive, we went to negative, minus infinity and infinity. Here, there is still one step we have to go back. Okay, good. So sorry, it doesn't go advanced. Okay, so yeah, again here, actually I think I uploaded the new one. There is so we cannot directly calculate a standard error of the risk incidence rate ratio. If we want to calculate a standard error of incidence rate ratio, we have to use an approximation method. It calls delta method. So I'm not going to go over that. This is approximation based on Taylor expansion. Here I use some of the fit incidents using that. So you can look at this code. I just did it, but I didn't put a lots of things, but this part is optional. There is a marginal effect that you can calculate, which is the change of outcome for change of predicted value for average over all the values. So is a little confusing, it's a little mysterious for me, this marginal effect. So hopefully Andy can explain it, but I don't think we have time. We need another workshop to explain marginal effect, okay? So that's something, but I defined it here. This is the number of visits made to doctor increased by this for each year of age when at work set is at mean. Set at its mean. So, and then there is average marginal effect, right? So this kind of thing, so you average that effect for each person. So basically you put everybody, assume they are at work, and then you calculate the outcome, and then you assume everybody not at work, you calculate the outcome, predicted outcome, and you take the difference, and then you average over. So those are the part as is the optional. Exposure, I put it as an option. Really, I don't have time, but in here, you can see one example. Basically, log of exposure is basically offset, right? So in this example, there is a data that has number of cases and then number of dies. So you can look at that. I'm sure you get it. So if there is more cases, the number of die, of course, is more, right? So that is basically our exposure. So log of exposure in GLM model is simply for exposure, you add log of that exposure as offset. And then you run the model, and There is more on that again. And there is overdispersion, that how we can deal with that. There is different way. There is a, basically, you can use the robust standard error to a little bit take care of that deviance. And then if it's a lot more variation that you are not explaining by that likelihood function, then you can add different type of model. So it's a little explained here. Don't reference that, okay? So don't reference this page as your reference. This is not a paper. So I wrote something here that is still mysterious for me. The reference, my reference was the regression analysis of Kant data by Colin Cameron and Praveen Trivedi. But however, these things that I wrote here in different software interpreted differently. So very careful on that, okay? Every day I find something that it doesn't make sense in different software. If you want to run the negative binomial, you can use, there is GLM, but you can use package mass. Oh, there is a bootstrap standard error. Yeah, you can use package mass as is a GLM NB, that is negative binomial model. But there is different type of negative binomials, but this is actual negative binomial, I think. So that's for that. I did some exercises using weighted least square. You might find it interesting. Basically, the way they estimate, I will answer that. Just give me a second. Based on the weighted least square, they estimate that parameter using iterative reweighted least square. So I explain it a little bit here if you are interested in computational statistics. And thank you. That was my workshop.